Here's how to set up a common emitter amplifier using some approximations to calculate all the resistors as well as capacitors. The idea is to set up a voltage divider bias on the base of the transistor to establish a DC operating point with no AC input signal so that we can have maximum output voltage swing, and we can take a relatively smaller input signal and have an inverted amplified output. We need to either know or just choose some of our design requirements, such as I'm going to assume I'm going to take the output signal, connect it to the input of another circuit stage that's going to have a very high impedance, maybe around 1 meg, and the output impedance of this amplifier circuit is basically the value of the collector resistor. So if I had a requirement for a certain output impedance spec, I could just choose my collector resistor value to suit that and then calculate everything from there. But if I'm going into a large impedance on another stage, this isn't so critical for me. What I will define arbitrarily is the collector current at the DC operating point. I'm going to say my collector current is about 2 milliamps. So I'm going to have about 2 milliamps flowing through collector and through emitter, getting this transistor into the active region. I would usually choose somewhere between 1 and 10 milliamps because I don't really need to drive a lot of load current. I just need the transistor to be operating and have its beta value closer toward its typical datasheet value. This emitter resistor helps this circuit operate more stable and linearly and minimally dependent on changes in beta and temperature, things like that. For example, if somehow we get some extra current flowing in the emitter due to temperature changes, we will develop a higher voltage across the emitter resistor, and we're holding the base voltage here relatively constant with this voltage divider. So if the emitter voltage increases, there will be a slight change in base to emitter junction voltage. That will change the emitter current and bring that emitter voltage back to where it used to be. So the emitter resistor provides a form of negative feedback to keep things stable, because different transistors, even from the same manufacturing batch, can have different betas, and beta can change over temperature. We can have changes in the emitter and collector current if we have supply voltage changes, so everything is a lot more stable in this configuration. Generally, the voltage across the emitter is at least several hundred millivolts, and one rule of thumb is 1/10 of supply voltage. I have 9 volts supply voltage in this case, so I'm just going to choose an emitter voltage of 1 volt. So voltage across emitter resistor is 1 volt, and from here I can calculate an emitter resistor to use. So that will be 1 volt divided by 2 milliamps, which equals 500 ohms, and the closest resistor value to that would be 510 ohms. The next thing I want to choose is what voltage do I want on my collector output at my DC operating point. So for maximum voltage swing, I want this to be maybe halfway between my positive supply rail 9 volts and the emitter voltage, which I've defined now as 1 volt. So I will choose the collector voltage to be 5 volts, because then I can go 4 volts positive toward 9 and 4 volts negative from there toward the emitter 1 volt. Now I can calculate the collector resistor, the voltage across it. 9 minus 5 is 4 volts divided by my current of 2 milliamps. So that would be a 2K resistor. Now we can work backwards and figure out R1 and R2 to get the required base voltage to set up this DC operating point with 5 volts on the collector and 2 milliamps of collector current. We know we now have 1 volt at the emitter, and the voltage at the base emitter junction is around 0.65 volts. So the voltage at the base is going to be around the emitter 1 volt plus 0.65, so the voltage across R2 is 1.65 volts. So now we need to decide what current we want flowing through this voltage divider so we can calculate a resistor value. We have 2 milliamps emitter current, and the emitter current is beta times base current. So if we assume beta to be 100, the base current is 2 milliamps divided by 100, or 20 microamps. Now, knowing we have a base voltage of 1.65 volts, in order to keep this voltage set by these two resistors stable regardless of changes in base current, we want to make sure the current flowing through this voltage divider is at least 10 times the base current. So I'm just going to make it 25 times base current to make sure this is stable. And because this current in these two resistors is much larger than the amount going into the base, I'm just going to assume the current in R1 is the same as the current in R2. So 25 times the base current of 20 microamps is 500 microamps. So now I can calculate R2 and R1. R2 is going to be the base voltage, 1.65 volts, divided by the current through this voltage divider, 500 microamps. That's 3.3 K. R1 is going to be 9 volts minus 1.65 volts divided by 500 microamps, which calculates to 14.7 K. So we choose 15 K as a standard value. Then we can use the voltage divider equation to recalculate what the base voltage is because we're not using calculated resistor values. So the voltage at the base will be 9 volts times R2 divided by R1 plus R2. So it's actually 1.62 volts instead of 1.65, which is still very close. So at this point, using these four resistor values at 9 volts, we should get these operating voltages relatively close, even as we change transistors and have different beta values and so on. And another calculation we can make, the gain of this amplifier is going to be the collector resistor divided by the emitter resistor. And it's going to be negative because it's an inverting amplifier. And with a 2K resistor divided by 510 ohms, this is 3.92. And to help make it a little easier to prototype, I made this NPN transistor dev board with today's sponsor, PCBWay. So for a bunch of the components, instead of soldering them directly to the board, I use these machine pin sockets. So I can swap in different resistor values, different capacitor values, and I can easily take the transistor out of the socket and swap in a new one. And there's a bunch of headers here for a breadboard, so I can power the board, send in a test signal, and get the output signal all on the header pins. So I can just plug this into a breadboard and have this self-contained module. Sometimes trying to just build the simple circuit on a breadboard, the parts are too close together, or the leads may touch and short out a lot easier. So this may sometimes help with that, but if a standard circuit block is designed, then I can just commit the part values on here and plug this board in when I need a quick transistor amplifier circuit. So I have an NPN transistor, I have resistors for a voltage divider bias, an emitter resistor, and a collector resistor, space for capacitors for input and output, and then there's other optional components. I can put a 1 meg resistor to ground on the input to give the input capacitor a ground reference. I can also set this up with an output off of the emitter if I want, and I have a header pin for that. I can put an emitter bypass capacitor on the emitter resistor, and if I want, I can split the emitter resistance into two separate resistors where one has a bypass capacitor and there's still a fixed resistor in circuit. So that can give us a DC operating point as well as some AC characteristics. And for trying a circuit that doesn't have a voltage divider bias, this top resistor isn't tied to the positive supply, I can put a jumper to positive supply, or I can jumper it so it goes across to the collector for a different feedback structure, or I can tie it to a voltage reference, which I can set up with resistors here. So I just wanted a somewhat universal configurable transistor development board. This is the transistor circuit on the PCB. I have some NPN transistors set aside. I took them out of one of these kits, so I'm using a couple of 2N3904s and 2222s and one S8050. So I have the S8050 in the tester, and it says the beta is 287. Of course, that's tested at certain conditions of voltages and currents on this tester, but I'm just looking to get an idea where these are at. The second one is a 3904 with a beta of 215 on this same tester. I checked the other three, so we have a beta of 216, 433, and 216 again. So that's a 2N2222, 3904, and 2222. We have 9.04 volts or so as our power rail. Now, checking the voltages on the emitter, we basically have 950 millivolts with a calculated 1 volt expected, so that looks good. And our base voltage, 1.6 volts, and the collector, 5.3 volts. We're expecting 5 volts, but give or take a couple of hundred millivolts from calculated. As long as it stays relatively stable as we switch transistors, we're just looking to get relatively centered between our voltage rails, or whichever two extremes we decide to calculate between, so that we have maximum headroom with some variance expected for practical circuits. So now if I take out that S8050 transistor and I take the second one, which is a 2N3904 with a beta of 215, the previous transistor's beta was 287. Now the emitter is around 910 millivolts versus the 1 volt calculated. Base voltage 1.59 or so. And the collector output 5.44 volts. This is the 3904 with the huge beta I measured of 433, 948 millivolts emitter, 1.59 volts base, and 5.24 volts on the collector. So even with that huge difference in beta on that transistor, we still have around the same operating point at our collector. Now on the signal generator, I have a sine wave at 1 kilohertz. So if we were to calculate the gain, and it's inverted, obviously, the output is inverted from the input, but if the gain we calculate as around 140 millivolts RMS divided by the input of, say, 37.5 millivolts RMS, 140 divided by 37.5, a gain of around 3.73. And if we use our gain approximation of collector resistor divided by emitter resistor, we have 2K divided by 510 ohms in my circuit. 3.92 is the gain that we calculate with our estimation. And now if I take away whatever that transistor is, that one had the beta of 216. So if I go back to the one with the huge beta of 433, the numbers are looking the same. We have like 140 millivolts RMS, and of course we still have 37.5 or whatever millivolts in. And even with two different transistors with way different betas, we have our consistent gain performance. Now for AC signals, we can increase the gain beyond this calculated 3.92 by adding this bypass capacitor across the emitter resistor. So for AC signals, this becomes essentially like a short circuit to ground from the emitter, and with the emitter resistance being very small, Now we have to factor in an equivalent small emitter resistance, which we're writing as small Re. So this is related to transconductance, and once all the equations are simplified, this effective emitter resistance is equal to thermal voltage, which is around 25 or 26 millivolts at room temperature, divided by collector current, which is 2 milliamps. So there's about 12.5 ohms of inherent emitter resistance here. So now our gain can calculate out to collector resistor 2K divided by 12.5 ohms. That's a gain of 160. And we may not want that much gain, so one thing we can do is, instead of using a capacitor directly across the one emitter resistor, if we replace that emitter resistor with two resistors and have only one of them bypassed, we can just choose a resistor so that our 2K collector resistor divided by this other non-bypassed resistor gives us an AC signal gain of something smaller than 160 that won't cause our amplifier to distort. So to determine a capacitor value for this emitter bypass, one approach is to make the reactance 1/10 of the emitter resistance or less, so that when this reactance is in parallel with this emitter resistance, it becomes a much smaller impedance. Reactance is 1 over 2 pi, and then the lowest frequency of interest, let's say it's 20 hertz, times capacitor value. We could say we want XC to be 510 ohms divided by 10, so around 51 ohms or smaller. We can just pick a number, calculate what capacitor value gives us that reactance. The larger the capacitor, the smaller this overall external emitter resistance will be. So now I have an emitter bypass capacitor. And I've also changed the input frequency, so I'm at 100 hertz. The input is still around 37.5 millivolts RMS, and the output is now 1.5 volts RMS. So calculating the voltage gain, we have 1.5 volts RMS divided by 37.5 millivolts RMS, a gain of about 40. With this capacitor now as part of the emitter impedance, we need to calculate its reactance at 100 hertz and 47 micro. Calculate that in parallel with this 505 ohm resistor. So XC is 1 over 2 pi FC. So 2 times pi times 100 hertz times 47 micro, 1 over that. The capacitor has a reactance of 33.8 ohms, and now that is in parallel with a 505 ohm resistor. So this times 505 ohms divided by this plus 505 ohms, we have 31.7 ohms of emitter impedance here. And 31.7 ohms is relatively small, so now we need to factor in properties of the transistor, taking into account the transconductance. We need to calculate the impedance we're seeing looking into the emitter of the transistor and put that in series with this external 31.7 ohms. So the resistance looking into the emitter of the transistor is thermal voltage around 25 millivolts divided by our collector current. We calculated it to be 2 milliamps, but to check what it actually is, assuming the emitter current is the same as collector, we'll just calculate the current, 941 millivolts divided by the 505 ohms. So we have 1.86 milliamps of collector current. So the impedance looking into the emitter of the transistor is about 25 millivolts divided by our collector current, 13.4 ohms. Adding that in series with our external impedance of 31.7 ohms, we have around 45 ohms of emitter resistance to factor in. So now if we want to calculate the gain using the estimation of RC, collector resistance 2K, divided by emitter resistance, we have an estimated gain of 44. So that's in the ballpark of our measured gain of 40, just for using approximations. And because we don't want our established DC voltages to make their way to another circuit stage, or for any other circuit stages to interfere with our DC voltages, we have a series DC block AC coupling capacitor with our input and output. So to figure out a good value for those, again with the output, I would plan to hook this up to some other input stage with a very high impedance. Let's say it's 1 meg to ground impedance. So the output signal will have a source resistance of our collector resistor, in this case 2K, but that's going to be way less than the high impedance I'm connecting this up to, so I can ignore this signal source resistance. So then we have a high-pass filter with a capacitor and then a very high impedance to ground. So if my lowest frequency of interest will be 20 Hertz, where I want to calculate a minus 3 dB filter cutoff, I can just substitute in 1 meg arbitrarily. So then filter cutoff 20 Hertz equals 1 over 2 pi resistor, large 1 meg, times capacitor. So I can solve for capacitance to give me that sort of frequency response. On the input, we also have a high-pass filter. We have this capacitor, and then from an AC perspective, R1 sees an AC ground at the 9-volt rail, and we already have R2 to ground, so R1 is in parallel with R2, and that is in parallel with looking into the base of the transistor to ground. And that is going to be the emitter resistance reflected over to the base by multiplying emitter resistance by beta. So emitter resistance times 100 in parallel with R1 and R2. And if we're using a bypass capacitor here, let's just say this external emitter resistance of 510 ohms is a short circuit for AC. We still have this inherent resistance, 12.5 ohms, times beta, let's assume it's 100. So we have 1.2K resistance to ground in parallel with R1 in parallel with R2. Then again, if we want to say our minus 3 dB filter cutoff is 20 Hertz, we can solve for the capacitance here with 20 Hertz is 1 over 2 pi, these three resistances in parallel, times C, and solve for a capacitor. So in this case, 15K in parallel with 3.3K in parallel with 1.25K. That'll give us around 855 ohms of input impedance. Now solving for C, that's close to 10 micro. And we wouldn't need that much capacitance on the output capacitor in this case, but we can still use it. And whatever gain situation we wanted, we would just choose whatever the emitter bypass capacitance is, and there's our circuit. So that's one way to make use of all of these simplifications once we know a few things about how we want the circuit to operate and get it up and running and functional.